polynomial functions. So transformations of polynomial functions, we've done all the transformations that we're going to do. Remember how I said you're going to use it throughout the course because we have other types of functions to learn about. We've already learned polynomial functions twice actually, last year in math and 20 IB and then last unit, the first unit of the course. And so now we're just looking back how to sort of do the proper transformations per se in transformation form with polynomial functions. Okay, and then the next unit, radicals and rationals, we'll use transformations of those. So a different aspect of when we learned those back in math 20. And then we'll spend about a month on trig, doing transformations of trig functions, and then exponentials and logs. Okay, so in every unit, we're going to go back to transformations. So in this one here, it says we've got a qubit. It was transformed to get the graph of that function. Describe the transformations in the correct order that were made on y equals x cubed. So this is in terms of x, it's not in function notation, right? But you remember how you get that is, remember this is, you can put a circle around it, that's what's cubed, right? So obviously, x was replaced with x plus 4. There was a number in front, so this is like your f of x. This number in front is a vertical stretch by a half, reflection in the x-axis, and then up 3. Okay, so you have to compare it to your original graph. You've got to state your stretches first. So this would be a vertical stretch by a factor of 1/2 about the x-axis. Okay. Then the negative with the half is a reflection in the x-axis because you're changing the sign of y. So positive y becomes negative. Negative becomes positive. So it's over the x-axis. And then you can do a vertical translation. Up 3 and a horizontal translation. Left 4. Okay.
So this would be one of the cases where a horizontal translation is a vertical translation and horizontal is not a thing. Reflection about the y-axis can be changed to reflection about the x.
Yeah, exactly. So we're going to look at that. We're not going to look at the reflections, but we're going to look at the stretches later in this note. Okay, so the point -4, -64 lies on the original. Determine it on the new graph. Now, important that you don't just take -4 and substitute it into the new graph. That's not how you do it. You take the point and you perform the transformation. You want to know the image of that particular point, not the point on the new graph with x equals -4. Okay? So, this point here, if we're doing these transformations, so we start with that. Vertical stretch by a factor of a half. You multiply your y value by a half. You don't have to show all the steps. You can go straight to your answer, but I am showing it through each transformation. Then a reflection in the x-axis makes that positive 32. Vertical translation 3 up would be 35. And then last thing, horizontal translation left 4 would be -8. Okay. Now, you can check that, put show it algebraically, we'll substitute in. So negative 8 plus 4 is negative 4. Negative 4 cubed is negative 64. Multiplied by negative 1/2 would be positive 32. Plus 3 is positive 35. Okay? So check it. All right? So don't just leave it. Complete the mapping. So in general, what's happening? So I'm just going to make sure I got this. Vertical stretch by 1/2. Actually, do this. So vertical stretch by 1/2. Reflect in the x-axis. Then translate 3 up and left 4. Okay. All right, so graphing that. Now that we know transformations, we can take important points from our original graph and do the transformations. If you didn't know transformations, then probably you do a table of values, right? And substitute values in. But let's practice our transformation skills. So obviously this is an important point, right? We call that a point of inflection. It passes through the origin, changes from what we call concave down, so sort of opening down to opening up. Okay? And it's a cubic, right? We talked about that when we were talking about multiplicities. So here, take that point, vertically stretched by 1/2, doesn't change it, reflected in the x-axis doesn't change it, then we need to go up 3 and to the left 4. Okay? Unfortunately, we didn't give you that much good paper for this, so we're not going to do that forward, but that's going to be your point of inflection. Choose a couple more nice points. So for sure, this is a nice point and this is. They're on, by nice point, I mean on a grid crossing, right? Then you know they're integer values. So this has a y value of 1, multiplied by 1/2, reflected is negative 1/2. Okay? Then we're going to go up 3, 1, 2, 3, to the left 4. 1, 2, 3, 4. Okay? And think about what it's going to look like, right? So we know it's been stretched vertically by 1/2. That means it's going to look squished, compressed, right, vertically. So this here, and it's reflected, is going to be shorter vertically, right? So this is going to kind of go like this. That's your point of inflection. This point here will then be over here. You can quickly go through it, but y is negative 1, stretched by 1/2 is negative 1/2, reflected is positive 1/2, 1, 2, 3, 1, 2, 3, 4. Okay. And then maybe you want to choose these one more set of points. Those are nice ones. So here, 8 times 1/2 is 4, reflected is negative 4. Up 3 to the left, 4. Okay, and then we're going to run out of space here. So unfortunately, we don't have a lot of it's been a little bit crazy here. What is it? 8, 4, 1, 2, 3, 1, 2, 3. Okay. Same deal. That kind of like a parabola, the vertex of a parabola. You look at these two terms inside the bracket and outside. In this case, it's not for the vertex; it's for the point of inflection. So point of inflection is negative 4, right? So you could have found more points if you had more graph paper on the left if you needed more. You could expand it higher and find another one within there, but close enough. Okay. All right, question 2. There is a polynomial function called p of x. It's in factored form. Okay, it says what is the y-intercept of the polynomial function? If it was in simplified form, the y-intercept is a constant. If it's in factored form, do not expand it out. There is no need to. Y-intercept, remember, is when x is 0. So y-intercept, you can put in 0. And then really what you're doing is multiplying all the constant terms. So you don't have to show work for this. I just did there for you. But it's really going to be negative 4 times 1 times 2. Because there's nothing out front, which means a 1. So that's going to be negative 8. So the y-intercept is negative 8. Okay, so then think about it. If we are doing this transformation, okay, and we've got a y-intercept of negative 8, and we are replacing y with 1/2 y, that's a vertical stretch by 2, right? So if we have a y-intercept of negative 8, and we're stretching that by 2, that's now going to be negative 16. If our original y-intercept is negative 8, and now we're doing this transformation, so this is solved for y, so this is a vertical stretch by 1/4, okay? So then negative 8 times 1/4 is negative 2. Okay? Graphing calculator, let's get it out just to show you kind of a couple little tricks in here. So, let's graph the original. Just put it in factor 4. With a standard screen. Okay. Standard, you can't see that relative minimum at the bottom. If you wanted to change your window, what could you go to? Y, maybe negative, let's go negative 25, see if you can see it all. If you want to see the whole thing. Really, we only care about the intercepts, right? If you press trace, it often goes directly to the y-intercept. Okay, so that confirms what we said, the y-intercept is negative 8. Okay, so see it says, what's the y-intercept of this function? So remember in your calculator, you have to have y isolated, and it is there. So you could put 1/4 with all of those brackets in again, or what you can do is go 1/4, so 1 divided by 4, or if you have the fraction form, you can go 1/4, okay? And then put in y1. It will copy out whatever you had in for y1, which is what we want to multiply by, p of x. How do you get y1? Remember, it's bars, y bars, function. Okay, so bars, y bars, function. There's your y1. Enter it. There are some different ways of doing it, but this is the way I like to do it. Okay. Now graph. be compressed, right? Because we're multiplying by 1/4. So we call that a vertical compression. And so this maximum there would be half as high. This minimum, that would be, or sorry, not half, a quarter as high, as much, right? Because we're dividing by 4. Okay. So if you wanted to check, we could do, let's do minimum on my blue graph. So I'm going to do, you don't have to do this. I'm just going to do it so you can see. If I find the minimum point there, negative 24.19. If I quit out and copy y, which is here, alpha 1 is y. It takes the y value that your cursor was at on the graph. Okay. Let's divide that by 4. So let's see if that's what my transformed function, the red has a minimum. So now I'm going to go, trace minimum. I want to go to my red graph though, and it actually kind of went there automatically, but I'll do it to make sure. Okay, and then if I quit out of that, go alpha y, and you can see it's the same. Okay, so there's ways of checking that to verify this. Okay, so we verified using our calculator. All right. Okay, what are the zeros or x-intercepts of the polynomial function? So it's already in factored form. So it's whatever makes these zeros. So positive 4, negative 1, negative 2. Positive 4, negative 1, negative 2. You can put them in numerical order if you like. Okay, those are the x-intercepts. Okay, the zeros of that function. So what are the zeros if we replace x with 1/2 x? So that is a horizontal stretch by 2. So that takes every x value and doubles it. So 4 will become 8, negative 1 becomes negative 2, negative 2 becomes negative 4. Okay? Now I want you to actually find the equation of that transformed function. So this is going to be y equals, we're going to replace x with 1/2 x. And then remember it was a minus 4. Then we replace x with 1/2 x and it was a plus 1. And x with 1/2 x and it was a plus 2. Okay? That's the transformed function, but not in the form that we like to show. Right? Remember when we say express in factored form, we never want fractors or decimals in the factors. So that's the initial substitution, but then we want to rewrite the equation in this form. So notice how the coefficients of x are all 1s. Okay, so I'm going to give you a minute to do that. Think about basically a grade 10 factoring strategy or skill, but sometimes students mess it up. So rewrite that in a factored form with coefficients of 1 on x, not a half. This is the factor a half out of every factor. So that's really what you're doing. You're factoring out a half from here. That'll leave you with a bracket of x minus 8. Then you're factoring out a half from here. And then I'm going to show that. What's a half times a half times a half is 1/8. Now take a look at that form. And it says, what are the zeros of the transformed function? Okay. Oh, sorry, that's a different one. So here, I want you to take a look at the zeros of this. Well, are they the same as that? This would be x equals 8, -2, and -4. Exactly what you said they would be. Okay. This is the initial substitution. This is how we would want to show a polynomial function in factors form. We don't like to have factors. Okay, so if you're ever asked to take a polynomial function, express it in factors form after a certain transformation, then make sure that it's in, I've got integer terms and coefficients. Okay, so just do that work at the end. Okay, so let's do another transformation. What are the zeros of the transformed function if p of x was horizontally stretched by a factor of a half and then reflected over the y-axis? Okay, so back to your original p of x. So I think that's at the top of your page as well, right? Yeah, p. So there we are now. Oh, yours, I'm sorry, yours is a little bit different, right? No, they're good. Sometimes our notebook files haven't been updated to the notes, but this is the same. Okay, so here we want to horizontally stretch by half. So that means we're going to multiply each of those by half and then reflect over the y-axis so they change sign. So half of 4 is 2, change the sign is -2. Half of -1 is -1/2. Change the sign is +1/2. Half of -2 is -1. Change the sign is +1. Okay, write the equation of the transform function in terms of p of x. So that's just in terms of your transformations. So you start with, so y equals p of x is what you start with. Now we are horizontally stretching by a factor of a half. So I'm going to replace this with 2x. And then reflecting over the y-axis changes the sign of x. So I can put that right out front because really when you replace x with -x, that's where it's going to end up showing up. Okay. Now, in terms of x, you substitute this back in for every x in your original p of x. So that means it's going to be -2x minus 4, -2x plus 1, -2x plus 2. And again, we don't like having leading coefficients in factors that are negative. So want you to rearrange that. Notice how here, this says you have to have just x as the first term. +1x. These are all -2 x's. So do the appropriate factoring to get it out. Yes? That is the reflection over the x-axis. Yeah, y-axis. factor out a -2 for each factor. And in this case, you actually are going to have a fraction in one of them. So, and we're going to have to allow that because what we're told here is that the coefficient on x's has to be 1. Okay? So we have to follow this even though it's not the best form once we get that. So here, okay, and so -2 times -2 times -2 is -8. Right, so this is not like we want to show it, but normally, but in this case we have to because we have to follow the form that's given. And there is no coefficient in front of the x there, right? So we have to leave it like that. Take a look at the x-intercepts here then. -2, +1/2, +1. That's what we thought it would be. Okay? So, 2 thumbs up on that, right? Okay, a couple that are a little bit harder. So, if p of x were transformed to give that as our new equation, describe the transformations that took place. So I'm just going to copy out p of x here so it's easy to see. Okay, so you have to think about what you replace x with, basically. Like if you look at those factors and you find the x-intercepts of that transformed function, they're all the same as the original x-intercepts. So that means there's no horizontal stretch. So good news, after. So you factor everything out so that you can basically replace this with p of x. So we've got that there. That's p of x. Okay, so it's 8 times p of x. So that's a vertical stretch by a factor of 8. About the x-axis. Now, did you have to do that even? We knew by looking at this and getting the x-intercepts that they were the same as the original x-intercepts. what's the y-intercept of this function here? Well, all the first terms would go to 0, so it would be negative 8 times 2 times 4. Well, that's 8 times negative 8 is negative 64. Would be your new y-intercept. Okay? If you go back to your original y-intercept is, where is it? Y-intercept was negative 8. Okay? Your new y-intercept was negative 64. So obviously it had to have been stretched by a factor of 8. So, and that's what we thought it was. Okay? We did the math behind it here to express it in terms of p of x, and we got the same thing. So again, there's different ways of figuring that out. But by finding the y-intercept and comparing it to the original, that can get you a vertical stretch. Okay? Now, yes, there could be translations that get it. Maybe it isn't stretched by 8, and then it's translated, but we know it couldn't be translated because we got the same x-intercept. Okay. And then, oops. Oh yeah. It's cut off for some reason. So then 8. I'm just going to write it out there.
Okay.
Yes.
Did G have a reflection of the x-axis?
It's not negative 8. The original y-intercept was negative 8, and the new one was negative 64. So there's no reflection.
Oh,
Okay? So H, I had to write it in here because you'll need it in my file. So again, take a look at this transformed function. Compare it to the original, the x-intercepts here to the original x-intercepts. Are they the same or different? Are they different, or are they all by a certain stretch factor? Do the same for the y-intercepts. The original y-intercept was negative 8. What's the y-intercept of this? Negative 12 times 3 times 6. Figure out what that is. So, going from this to this is a horizontal stretch by 3. Going from here to here is a vertical stretch by 27. So since there's nothing to factor out from the x's, doing it this way, looking and comparing the x-intercepts and the y-intercepts, and then performing the transformations that we think it is on our original, okay, to see if we end up with that as our transfer function will be the easiest method. Rather than, on the last question, we could factor out, and then it was easy to see. But because of that vertical stretch, both stretches, there's nothing to factor in the original, in the image. So, from my original, y equals p of x, my transformed will be, from what I think it is, 27 p of 1/3 x. Okay? Vertical stretch by 27, horizontal stretch by 3. Now verify. So substitute that in and see that you get this. So we're going to have 1/3 x minus 4, because it was, and then 1/3 x plus 1, and then 1/3 x plus 2. Simplify that, or not by expanding, I should say, I guess, factor out the coefficients of x so that you have ones. Okay, we're trying to see if this is the same as this. So factor out 1/3 from each one. Simplify that factor with the 27. Make sure it goes away. Make sure it's 1/27. Right? And that your constant terms are the same. Well, that's going to be 27 times 1/3 times 1/3 times 1/3 is 1/27. And those divide out, and you get that factored form. So you know you've chosen the correct transformation.